If instead of having a series RLC circuit, we have a parallel RLC circuit, we can have the same type of idea with parallel resonance. So the basic principle is that, again, the impedances for the inductor and capacitor are canceling out when we're considering our equivalent impedance. We're not going to go through the detailed analysis, but if you're curious, you can look on pages 632 to 633 in the textbook. So here we're just going to present the results, and then you'll have a chance to get some practice in the homework. So through that analysis, what we find is that our resonant frequency omega naught for this parallel RLC circuit is equal to 1 divided by L square root of L times C, and again that's going to be in units of radians per second. So this we see is the same as what we had for series. So same as our series RLC circuit, same as for our series resonance. Some of our equations are going to vary a little bit. So we have equations for our two half power frequencies, omega 1 and omega 2. So for omega 1, we have that it is negative 1 divided by 2RC plus the square root. And in that square root, we have the quantity of 1 over 2RC squared plus 1 divided by LC. And then our omega 2 is going to be pretty much the same thing, but this term out front is just positive. So 1 over 2RC plus the square root, and then in the square root we have 1 over 2RC quantity squared plus 1 divided by LC. So there are equations to find our half power frequencies. We have that our bandwidth is equal to omega 2 minus omega 1. So that equation is still valid. We can also describe the bandwidth as 1 over RC. Our quality factor, so we have slightly different equations here as well. This is going to be omega naught times RC. Not sure what happened there. Let's clean that up a bit. So omega naught times RC. It's also equal to R divided by omega naught times L. Or we can find it as the square root of CR squared divided by L. Again, for all of these equations where we have beta, any equations that we have beta, we want to plug in using radians per second. One thing to note, and we've kind of already mentioned this, is that equations 1 and 7 through 10, shown in previous videos, for our series RLC circuit are still valid here. So still valid for the parallel RLC circuit. And I believe I've left off that list equation 4, and equation 4 is essentially just this one here, that the bandwidth is omega 2 minus omega 1, and of course that is also still valid for this parallel circuit. One other thing that I want to introduce here is just a couple alternate forms that you can use with either series or parallel. So alternate forms for series and parallel resonance. And so these are for our half power frequencies. So we can say that omega 1 is equal to negative the resonant frequency divided by 2q plus omega naught times the square root of 1 plus the quantity of 1 over 2q squared. And then, like with most of our equations for these half power frequencies, our omega 2 is the same. We just change the sign of this term out front. So omega naught over 2q plus omega naught times the square root of 1 plus a quantity of 1 over 2q squared. And so again, these last two equations are good for both series and parallel resonance, or series and parallel RLC circuits. And something to keep in mind again with all of these different forms of our equations is that we can choose the ones that are most appropriate based on the given information. And we can also utilize the various forms to double check our work if you so desire.